Okay, so greetings of the day to all the viewers and welcome in this session where today we will discuss a very important topic of electrical engineering, which is transformer. Now, why transformer is important? When we will study power system, we have seen that in power system there is something known as transmission of power. So for transmission of power, we need to use transformers to transmit power from one place to another. So that's why transformer is a very important topic. It is very commonly used device, and transformer can be of single phase transformer as well as three phase transformer. Today we will study single phase transformer. So first let's try to understand the working of a transformer. Okay, so transformer is a static device which has two electric circuits and one magnetic circuit, and it transfers electrical energy from one circuit to another without the change in frequency. So this is the basic principle of transformer. Now what happens inside the transformer is there are two things. First, we need to know about self induction and mutual induction, and we also need to know about Faraday's law and Lenz's law. So what does Faraday's law states that when there is a change in flux in the linkage, there is a change in flux linkage in the coil, then what happens? Then an EMF is induced. This is Faraday's first law of electromagnetic induction. And the second law states that the EMF induced is directly proportional to the rate of change of flux. Whereas Lenz's law states that the EMF induced will be induced in such a way that it opposes the source. Okay, means it will try that no more EMF would be induced. It will try to be induced in such a way that no more EMF would be induced. I hope I am clear. But what I am trying to say is it opposes the source. That's what Lenz's law states. That's why E is equals to minus N d phi dt. So this is Faraday's law and Lenz's law. We will use this in understanding transformer as well. So what happens in transformer, that when voltage is provided in the primary, means there are two sides to electrical circuits. We can name one circuit to be primary and the other one to be secondary. The side where voltage is provided, where source is provided, that side is primary, whereas the side where the load is given, that side is secondary. Okay, so the primary is where the source's voltage is provided. Due to the voltage, a current is induced in the circuit, in the electric circuit, and due to this current and flux is induced. Okay, flux is induced. Okay, and there are number of turns in the there are number of turns in the primary side. So when this flux links with the number of turns, an EMF is induced. Okay, this is induced due to self induction. In the primary side, the EMF is induced due to self induction, and this same flux is linked with the secondary side as well. Now if it is a practical transformer, we can say that there will be some leakage in the transformer as well. But if we consider an ideal transformer, then we can say that the same flux will be linked with the secondary side as well. There are number of turns, and due to those turns another EMF is induced. Okay, now if the number of turns in the secondary are more than the number of turns in the primary, then we can say that the EMF, a greater amount of EMF is induced, so it is known as a step-up transformer. And if the number of turns are low, then it is known as a step-down transformer. Now here in the board you can see there is an equation which is the EMF equation of transformer. It is 4.44 phi m ft. Okay, so 4.44 phi m ft. How do we derive this equation? We derive this equation from the equation that E is equals to minus N d phi dt. We just put the value that instead of phi we put phi m sin omega t, and from there this equation is derived. Here T is the number of turns, E is the EMF, and if we see E by T, okay, if we put E1 in place of E, then we will have to put T1 in place of T. So this E by T means voltage per turn or EMF per turn is constant. So this E by T is constant, so E1 by T1 is equals to E2 by T2, and from there we can say that E1 by E2 is equals to T1 by T2. That is your turns ratio. Okay, so this is what we can get from the EMF equation of a transformer. There is one more thing, which is the equivalent circuit of the transformer. Okay, equivalent circuit of the transformer, as you can see on the board. equivalent circuit of the transformer is something for which we need to know values referred to primary and secondary. Okay, so in the transformer we are considering a practical transformer, so there will be some resistance as well, there will be some reactance. So there will be resistance and reactance both in the primary and secondary side. Now we need to for our ease of understanding and for ease of calculation, we need to put all these parameters in the same side. So that's why we use the refer to primary or refer to secondary technique. Here the circuit diagram which you are seeing, the equivalent circuit which you can see on the board, that circuit signifies equivalent circuit referred to secondary. Okay, you can see that some values you can see that there is a value known as R naught by A square, and there is another value called H naught by A square. Okay, so these are referred to secondary, and since these are referred to secondary, that's why we have divided them by A square to change the value with reference to secondary. And if the values would have been referred to primary, then the secondary values means R2 or H2, that would have been multiplied by A square. So just the opposite. Okay, and similarly the current is multiplied by A, which is the turns ratio here, and the voltage is divided by A. Okay, next we have a phasor diagram here. So in the phasor diagram we have taken V2 as the reference phasor, and then we have I2 which is lagging. So I2 is lagging, means it is a lagging power factor. Okay, that's why I2 is lagging. V2 means it is the load is inductive, we can say, that's why it is lagging. So mostly we have seen that there is in case of load we can see a lagging power factor, so that's why we have used a lagging power factor here. So V2 leads and I2 lags here. So I2 will be in phase with I2 RE2. Okay, RE2 means the equivalent resistance, and the I2 is the secondary current. So that will be in phase with I2 RE2, and then I2 HC2, which is another voltage drop, that will be leading the I2 RE2. Okay, or that will be leading I2. So and the combination of this two, I2 RE2 and I2 HC2, the phasor sum of these two things will give us I2 ZE2. Okay, and then the combination of V2 and I2 ZE2 means the phasor sum of these two quantities will give us your final E2, which is the EMF. Okay, so this is how we can draw the phasor diagram. Two more things are there. When we have considered the equivalent circuit, we have seen a few parameters like the I naught, which is the no load current. Now the no load current is divided into two components here, IW and I mu. So IW is your active component of current or watt full component of current, whereas I mu is your reactive component of current or watt less component of current. Okay, so basically your I mu is the current component of current which produces the flux, or which is responsible for the flux, and I2 is basically your I2 R square, the loss which is there, that is due to the I2. There are different types of losses in the transformer because we are considering a practical transformer, we are not considering an ideal transformer, so there are different types of losses. Now for the segregation of these losses, we need to have some test. This test are known as open circuit test and short circuit test. There is another test which is known as regenerative test or back-to-back test, that I have not mentioned here, but here I have mentioned about the open circuit test and the short circuit test. You can see the diagram here. Diagram is very simple. We have a voltmeter, wattmeter and an ammeter, and in the OC test or the open circuit test, we have selected the low voltage side for the testing, whereas in the SC test, which is the high voltage test, we have selected the HV side for our testing. Okay, so the thing is for HV, why we have selected the HV side for the SC test? So we know that if the side, if it is the high voltage side, then the current would be low because power is constant. So if the voltage is high, that means the current is low. So if we are selecting the low current side or the high voltage side, then we can do the testing with the given apparatus, with the low rated apparatus that we have, generally that we have in the laboratory. So that's why we have selected the HV side in the SC test, which is the short circuit test. And what are the things that we get from this OC test and SC test? So from the open circuit test, we get the iron loss. From the iron loss, we can also get the IW and I mu. And from the SC test, we get the copper loss. And from the copper loss, we can also get your RE2 or HC2, whereas we can also get ZE2. And from there, if we just divide the values by a square, we can also get your RE1 and HC1 and ZE1. So this is how we can we can calculate the parameters which we have seen in the equivalent circuit using this open circuit test and short circuit test. So this was all about single phase transformer. There is one more thing which is known as voltage regulation. So voltage regulation is basically the difference between the no load secondary voltage and the full load secondary voltage. And when we need to do the per unit, we just need to divide it by most probably no load secondary voltage. So that's how we get the value. So that is a different topic. Hope this much I have been able to deliver properly, and thank you for your time. Stay safe and be happy. Thank you.